Today I will discuss two sample location problem. This is lecture 4 of non-parametric inference. This is lecture 4 of non-parametric inference. Suppose x1 xm be a random sample drawn from the population with continuous CDF fx and y1 y2 yn be another random sample drawn from the population with continuous CDF Fy. Now we want to test H naught Fx equal to Fy small x for all x versus alternative Fy small x equal to Fx x minus theta for all x and some theta not equal to 0. In this case, we shall consider Wilcoxon rank sum test or Mann-Whitney U test. Today I will discuss Wilcoxon rank sum test. Many non-parametric methods are based on ranks. In many practical situations, the scales used to get measurements are arbitrary. So that we would want our results to remain invariant under order preserving transformations of the observations. Rank test may also be used in cases where quantitative measurements are not possible. Now we define the jump function Ju as 0 if u less than 0, 1 if u greater than equal to 0. Now the rank of xk among the observations x1, x2, xm, which are all different, is Rxk equal to sum over h from 1 to m j xk minus xh, k from 1 to m. For example, suppose these are the observation. Now this is x1, x2, x3, x4. Now the rank of x1, this is 1, this is 2, then it is 4, 1 and then 3. In that way, rank of x4, for example, I consider 3. Now Rx4, this is equal to sum over h from 1 to m, h for m for 4, so this should be 4, h for 1 to 4, j 3 minus xh. Now j 3 minus 2, this is positive, so 1 plus j 3 minus 4 negative, this should be 0, plus, because 3 minus 4 is negative, minus 1 negative, so this should be 0. Next j 3 minus 1, 3 minus 1 is 2, which is positive, so this is 1, and 3 minus 3 is 0, this is again 1, because ju equal to 1 if u greater than equal to 0. So rank of 3 is 3. Similarly, if you are interested in another observation, say R 2, then this should be defined as j from 1 to 4, then j 2 minus xh. Again you see that 2 minus 2 0, j is 0 1, 2 minus 4 negative, so j 2 minus 4 is 0, again 1 and again 0, so this is 2. So in that way we can represent rank of xk as follow. For the general case, when there may be ties, the ranks are defined using the function Cu equal to 0 if u less than 0, half if u equal to 0, 1 if u greater than 0. Then then in terms of CU, this 2 becomes Rxk equal to 1 plus H not equal to K M C xk minus xh. This is 3 and this should be 4. Now consider an example. Say 3, 2, 2, 5, 5. Now this is x1, x2, x3, x4, x5. Now I interested in x2. So rank of x2 is equal to 1 plus h not equal to k is 2. H not equal to 2, m is 5, c 2 minus xh. So now this is 1 plus c 2 minus 3 is negative, so this is 0 plus then 2 minus x3, 2 minus x3 is c 2 minus 2 0, so this contribute half. C 2 minus 5, 2 minus 5 is negative, c 2 minus 5 is 0, again 2 minus 5 0, so this should be 1.5. Now if you arrange this in increasing order, so this is a tie of length 2, the rank is 1 plus 2, this is the average rank 1.5, 1.5, 1.5, so x2 is 1.5. Similarly, if you are interested in x4, then Rx4 equal to 1 plus h not equal to 4, 5, c 4 minus xh, so this is equal to 1 plus c 4 minus x3, 1 because 4 minus 3 is positive, then c 4 minus x2 again 1, c 4 minus x3, this is again 1, this is 4 minus x5, so this contribute half, so this is 4.5. see that this is the tie, the average rank is 4 plus 5 divided by 2, so this is 4.5. So in that way we can represent rank of any observation in generally in that way. In the case of tie, two is, that is Rxk is mid rank. Many two sample tests two sample rank test may be considered to be a linear functions, to be a linear function of certain indicator variable variables of the combined ordered sample such functions are called linear rank statistics. Now suppose x1, x2 xm be a random sample drawn from the population with continuous CDF. I already mentioned it previously. With continuous CDF, fx and y1, y2, yn be another random sample drawn from the population with continuous CDF FY. In the two sample cases, the ordered samples gives us capital N equal to m plus n observations. The ranks of the x observations in combined sample are Rxk equal to sum over h from 1 to m j xk minus xh plus h from 1 to small n j xk minus yh. K from 1 to m. And the ranks of y observations are yk equal to h from 1 to n j yk xh plus h from 1 to n j yk minus yh. K from 1 to n. By introducing the indicator variable Zi, where Zi equal to 1 if the ith random variable in combined ordered sample is an x and 0 if it is a y and I from 1 to capital N. The combined order sample may be denoted by a vector z curl equal to z1, z2, zn. A class of statistic denoted by Tn z equal to I from 1 to capital N Ai Zi, where Ai are given numbers and the vector of indicator variables is z curl equal to z1 zn is called the class of linear rank statistics. So, this is a class of linear rank statistics where AIs are given numbers and the vector of indicator variable is z curl, then this is called linear rank statistics, class of linear rank statistics. The AI are called weights or scores. Now, under H naught, that is fx, fy for all x, expectation of Tn, where Tn equal to sum over I from 1 to capital N Ai Zi equal to sum over I from capital N Ai expectation of Zi, this is equal to sum over I from 1 to capital N Ai probability Zi equal to 1. And Zi equal to 1 means if the ith random variable in the combined ordered sample is an x. So, and under H naught fx equal to fy, so total number of possible cases capital N, choose one which is equally likely under H naught, and total number of favorable cases MC1. So probability Zi equal to 1 is equal to M by capital N. So this is equal to sum over I from 1 to capital N Ai into M by N. So M by capital N equal to sum over I from 1 to capital N Ai. Now variance of Tn, this is equal to sum over I from 1 to capital N Ai square variance of Zi plus I not equal to J Ai Aj cos Zi Zj. Now variance of Zi, this is equal to expectation of Zi square minus square Zi. So this is equal to 1 square into probability Zi equal to 1 plus 0 square into probability Zi equal to 0. So expectation Zi square is nothing but a probability Zi equal to 1, and this thing is M by N whole square. So variance of Zi, this is equal to N minus M by N whole square, then N square M N, because N equal to M plus N. Now expectation Zi Zj, this is equal to probability Zi equal to 1, Zj equal to 1. So total number of possible cases NC2, and now Zi equal to 1, Zj equal to 1 means ith and jth random variables in the combined ordered sample is sample R and X. So total number of favorable cases is MC2. So this is equal to M into M minus 1 N into N minus 1, because so this is equal to expectation Zi equal to Zj. Hence cos Zj, this is equal to expectation Zj minus expectation Zj, this is equal to M into M minus 1 N into N minus 1 minus M by N whole square. So this is equal to M by N N minus 1 into N Mn minus N minus Mn plus M equal to N square N minus 1 minus Mn. So this is equal to variance of Zi is equal to, I already get, m by n square. So m by this is m by mn, small mn by capital N square, sum over I from 1 to capital N ai square, plus this is equal to minus mn n square n minus 1 sum over ai aj, I not equal to j, then mn by n square I think we take this portion common, mn n square n minus 1 n minus 1 sum over I from 1 to capital N ai square minus I not equal to j ai aj equal to mn n square n minus 1 n sum over I from 1 to capital N ai square sum over I from 1 to capital N ai square plus I not equal to j capital N ai aj, this is equal to mn n square n minus 1 n sum over I from 1 to capital N ai square minus sum over I from capital N ai whole square. Now I consider the null distribution, exact null distribution of Tn. The probability Tn z equal to r equal to the number of arrangements of mx's and ny's such that Tnz equal to R, and total number of possible cases is NCM. Under H0, NCM are total number of mutually exclusive, exhaustive and equally likely cases. So the exact probability Tn equal to R equal to number of arrangements of n x's and n y's such that Tnz equal to R divided by capital N Cn. Tn is a linear function of the identically distributed but dependent random variables Zi under certain regularity condition conditions Tn minus expectation of Tn divided by variance of Tn asymptotically normal 0 1 as Mn tending to infinity in such a way that m by n remains constant. All two sample rank test are for the same null hypothesis but different tests may be sensitive to different types of alternative for Wilcoxon two sample rank sum test. The null hypothesis theta equal to 0 versus alternative theta less than 0, that is fx equal to, this is fyx equal to fx x minus theta, where theta less than 0. For that alternative, if sum of x ranks in combined sample is too large. So we accept alternative, that is fyx equal to fx x minus theta, where theta less than 0, if sum of x ranks in combined sample is too large. Or if theta greater than 0, in that case, if the rank sum is too small, that is, if the rank of x ranks, if the sum of x ranks in combined sample is too small, and when theta not equal to 0 is accepted, if the sum of ranks of x is either too small or too large, and here the Wilcoxon rank sum statistics, test statistics, defined as Wn equal to I from 1 to capital N I Z I. That means in Tn, just take Ai equal to I. In that case, Tn gives Wilcoxon rank sum statistic, and you check that expectation of Wn is equal to m into n plus 1 by 2, and variance of Wn equal to m n n plus 1 by 12. These are under H naught. So I want to stop today. In my next class I will discuss Mann-Whitney use statistics. Till then, please stay with us. Thank you.